Hi class, we are going to go over the next video in our series, which is chapter 10.1, which covers inner products. Now, we've seen inner products quite a bit already. This section will look very familiar to you. We're basically going to do all the same things that we did in the dot product section, but now we are going to extend the idea into sort of a wider play area, I guess you could say, right? So the dot product is a type of inner product, okay, but it's meant specifically for vectors inside of Rn, okay? Another name for the dot product is the Euclidean inner product because it acts on standard Euclidean geometry, okay? So what we're going to do is we're going to talk about inner products in other vector spaces, basically, okay? So the Euclidean space is the standard vector space that we work with. When we covered the vector spaces portion of the course, we looked at several different other vector spaces. So if you're in a different type of vector space, you have a different definition of an inner product. Okay, so that's really where we're headed to with this section. So all inner products satisfy certain conditions, and that's where we're going to start with. So I'm not going to give you guys a lot of examples, but we are going to do some proofs in this section. Okay. So again, one more time, everything we're doing right now is analogous to the dot product. We're just extending the idea to other types of vector spaces. Okay. So let's go ahead and get started. So let's start off with the definition. This is our definition of a dot product. Of an inner product. It is semi-heavy on notation, so we'll go a little slow and work through exactly what these things mean. Okay. An inner product acts on a vector space. Okay. It's a function. It takes something in and it will give you something out. We've seen before with the dot product, with the Euclidean inner product, that it gives you a scalar value out, and that's exactly what an inner product will do. Okay. You'll have some function. Okay. These dots represent my inputs. Okay. Anything within these brackets are the two things that the inner product is acting upon. The inner product acts on these two elements. Okay. In this case, they're dots. They could be functions. They could be polynomials. They can be vectors. They can be matrices. These dots are just basically placeholders, like a variable a is a placeholder for some number, right? So you take two things, and the inner product between them is symbolized by these two brackets. Okay, it takes two things from your vector space. So one dot comes from this vector space, the other dot comes from the same vector space, and it will multiply them together, and it will give you something in R. So this is your domain, and this is your range, right? You're taking something from your vector space, two things from your vector space, you are multiplying them together, and you're getting something in your range, which is a real number. Okay, so this is an inner product on a vector space V. Two things from your vector space multiplied together by the inner product will give you out a real value. That is what this says. Okay, so again, the function takes two vectors from V. And again, your vector space determines what your vectors look like. If my vector space is the space of all 2 by 2 square matrices with determinant that is not 0, right? Then the things that I am applying the inner product to will be 2 by 2 vectors that have a determinant that's not 0, right? So again, we're not in the standard applying these dot products to vectors. It's an inner product. It's generalized across basically all vector spaces, right? And so our vector, the thing that we get out will be something in R. This should be a bold-faced R, not just a regular R. Apologies for that, you guys. I'll fix that in the write-up. You get a real value out. So you take two vectors, you'll multiply them together, depending on the form of the inner product, and you'll get a scalar value out. Okay. So like the dot product, which is a type of inner product, right? So this is just, again, relating what we know already to this generalized idea of a general inner product. Okay. So let's do a theorem. Okay. So let's say that we have 3 vectors from our vector space and a scalar. Okay. Then these are the properties that hold for an inner product. Okay. The inner product between u and v is the same as the inner product between v and u. So again, just think of dot product when you think of these, okay? But again, we're just going to start defining them different ways. So for dot product, we had the same thing, that it was commutative, that u dot v was the same as v dot u. The difference here is it's just any inner product, okay? Here, if I take the inner product with u plus v and w, the w distributes into this addition, okay? So u plus v inner product w is u inner product w plus v inner product w, right? So again, analogous to what we had for the dot product, okay? Here, if I have c times u inner product with v, I can pull the constant c out times the result of my inner product. And the last one was that u inner product with itself will always be positive, and the only time it is 0 is if the inner product with itself is 0, and that only happens if my vector in this case is the 0 vector, right? So again, remember, the 0 vector depends on what your vector space looks like and how you're defining addition, subtraction, and scalar multiplication, right? So now we're really applying all of the things we've talked about before, obviously again, into this idea of inner product. Okay, so a vector space that has an inner product defined on it is called an inner product space. Okay, we are generally in applications, quantum mechanics, least squares analysis, all these things that we do generally, we are generally interested in an inner product space. Okay, a vector space is important. That's the world that we live in, that we do our math. But the inner product that's defined on that vector space is really what makes everything work in a particular way in that vector space, right? So an inner product space is a vector space that has an inner product that satisfies these conditions. Okay, so that's what we're going to be doing here. We will obviously be doing lots of inner product stuff, but we will definitely be proving that something is an inner product on a vector space. Okay, so that's what our example is for today's class. So I had to throw this in here somewhere so you can read it on your write-out and your write-up, but the dot product is called the Euclidean inner product. Okay, so again, the regular R2, R3, R to the n, that's the standard Euclidean geometry. So that dot product that is in the standard Euclidean geometry is called, it's basically the standard inner product, right? So we call that the Euclidean inner product. So let's look at some examples of some of the standard inner products. That does not mean that this is all of the inner products. Again, an inner product is anything in a vector space that satisfies these conditions. So these inner products can be tweaked and adjusted to fit whatever it is that we need it to fit in the world that we're working with. So the first one that we have is, given I have D in Rn by n, so that means that D is a square matrix and diagonal. In this case, it has to be a diagonal matrix with positive entries along its diagonal. Okay, so we have positive entries along the diagonal. Then the inner product that goes from Rn to Rn, so I'm going from the standard Euclidean vector space, right, of Rn to a scalar, is the inner product defined by U inner product V is U transpose D times V. Now this is actually very, very close to the standard dot product. Okay, so normally this D is not here. It actually is there, right? So our definition of the dot product was U transpose times V. So that D is actually there in the standard dot product, but it's the I matrix. It's the identity is the square identity matrix. Okay, so it doesn't do anything. So here, if the values along the diagonal are not all 1, then we call this the weighted dot product. Okay, so that's what this is. It's a weighted dot product. And the weights are determined by the diagonals of this diagonal matrix D. Okay, so when this diagonal matrix is the identity, it doesn't even matter if I put it here or not, because it doesn't do anything, right? The weights are evenly distributed across each term that you're adding against. Okay, here the weighted dot product, you're putting weights differently across the terms that you're adding together. Okay, so this can be used in something like grades, for example. Okay, if I'm trying to compute grades and I have your scores and I put those together as a vector, okay, as a single vector for, you know, your, I don't know, for all of your homework total, your discussion total, your classwork total, your homework total, your exam total, all of those are one entry. If my diagonal entries in my diagonal matrix correspond with the weights associated with your final grade, I can then do a dot product on your grade vector weighted by this diagonal matrix, and it will give me out your final grade. Okay, so that's one use of a weighted inner product, okay, in application. Okay, that's the most easiest one because it's a dot product, right? So that's one. Okay, 2, this is saying that we have variables in R that are distinct. So if we had an x vector, these would be single vectors and an x vector. Okay, so each of these are real numbers and they are distinct. There's no common terms here. Okay, this could be 1, 2, 3, 4, whatever. There's no repeats. Okay, then the dot product from the polynomial space of nth degree to the polynomial space of nth degree will give you out a real value, is an inner product if you are taking a polynomial of at most degree n times, inner product wise, another polynomial of degree at most n, and then you multiply them together in this way. Very, very similar to the standard dot product, right? Where you're taking the polynomial evaluated at each term and you are adding, or I'm sorry, multiplying those respective terms together and then adding them across to get a single value, right? So I'm plugging in x naught into my first polynomial and into my second polynomial, figuring out what those values are, multiplying them, adding them to the same thing with the next value that I'm interested in, and so forth and so forth. Okay, so this is commonly used in like a least squares regression, right? So the next one that we have is an inner product from a square matrix and a square matrix. Okay, so our vector space is the square matrices, and then we go to a scalar given by square matrix A. Inner product square matrix B is the trace of the product A transpose B. Okay, so we would take A, transpose it, multiply it by B, and then take the trace of that, and that defines an inner product. Okay. The next is one that we've seen in this class a couple of times, not as an inner product, but we've done some proofs around this. Is if I have an interval, closed interval from A to B in the real number line, okay, then if I'm looking at the smooth function, so again, a smooth function is a function that is continuous on A to B and is differentiable, in this case, at least once. Okay, so it's continuous and at least once differentiable from this interval to the real number line. So I'm taking two things from this space and multiplying them together to get out a scalar. I can define this by the inner product between a function on that space and another function on that space, and taking a bounded integral. So remember, if you bound an integral from A to B and evaluate it on those bounds, you will get out a single value. Okay, and so that inner product is defined by the integral of the product of f of x and g of x, and we can again tweak all of these things in several different ways to have variations of our inner products, right? So let's do an example. So when I say do an example, I don't mean I'm going to calculate a bunch of inner products, because again, the way I define an inner product is different in all these places. So what we're going to do is we are going to prove that something is an inner product, right? And I'm definitely going to ask you guys to do that at least once or twice in this class, right? So let's prove that the fourth one is an actual inner product. Going through a proof of this is actually maybe better than doing an example, because as you go through a proof, you have to run through all of these properties, right? So what does it mean to be an inner product? It means that these things are true, right? So I'm going to take three elements from my vector space and a scalar, and I'm going to apply these four properties and show that they are true. Remember now, in general, I'm not just going to take, oh, I want f of x to be 2x squared, and I'm going to make g of x be x, and I'm going to show that it works. That's not showing something as a vector. That's showing that a specific example is a vector space. We need to do this in general for any function from my vector space and any scalar from R, that these properties hold if I define a vector space the way that I do here. Okay, and that's what we're going to do. So let's go ahead and start that. All right, so we always start off with the things that we need, right? So let's go to this definition. I need an interval. I need some things from my interval, and then I can get started, right? So I need to have an interval that exists, right, on R. So from A to B. I'm going to define my inner product from f of x and g of x as the following, right, which is our definition of an inner product. So that's going to define my inner product in the smooth functions from A to B. So I need three elements from my domain, right, the smooth set over A to B. So I need f, g, and h that exist on that interval. So that means that these three things are continuous on this interval, and you can differentiate them at least once, right? And I have a scalar that I need also. Okay, any scalar, it doesn't have to be on this interval, just a scalar, right? So what does that mean? Well, let's look at the first one. What does it mean to have f of x and g of x, right? Well, if I take this integral, and then let's say I switch the order around, it's the same thing. And me switching the order around is just like me switching the order around inside of that inner product. Okay, so I real easily showed that this is commutative. Okay, it commutes. F of x and g of x is the same as g of x and f of x. Right? I showed what this is, and I showed that it's the same as that. Very, very straightforward. Okay. So again, I'm not taking a specific function, any function, as long as it exists over here. And then now I'm going to just start playing around with this integral using the rules of integration. So now I have the inner product of f of x plus g of x and h. So what does this look like? Well, the first thing here is not f of x and g of x and what have you. The first thing I'm going to have is this. That's my first function plus, times this function. So parentheses, the thing in my first space, right, times the thing that I am inner producting against, right? So parentheses f of x plus g of x. And again, it's always a good idea to know where I'm trying to go, right? So where am I trying to go? I'm trying to get the inner product of f of x and h of x plus the inner product of g of x and h of x. So I'm just going to manipulate this until it looks like that, right? So I can distribute this h across that parentheses. Okay, I still have parentheses here because this is one integral still, right? But integration you can separate across the sum, right? So now I have f of x and h in one integral, g of x and h of x in the other. And what do you know? That is exactly what this looks like on the other side, f of x and h plus g and h. Not g and h, but inner product with h, which is what I needed to show, right? So that's that second property, right? Here I have c times f of x and g of x. So I'll have this times this inside of an integral from a to b, okay? And we know that when we have something like this, we can pull the constant out. So what is that left with? A constant times the inner product of f and g, right? So again, these aren't too hard to do. You just have to be familiar with starting somewhere and trying to get somewhere else, okay? So I have proven then that this is the same as this. That I can pull out a constant from this definition of an inner product. So we got one more thing to prove. So remember, the next thing is that the inner product with itself is positive or 0, and the only way that it is 0 is if the thing that I am inner producting with itself is the 0 from my vector space anyways, okay? So I have that this looks like the integral of f of x times f of x, which is the same as the integral of f of x squared, which is always positive, because if I plug something in here, it'll be positive, right? So integrating an always positive function will always be positive or 0, but the only way that this is going to ever be 0 is if this thing that I'm squaring is 0 itself. If it's not 0, it'll always be positive, right? So if my function is 0, then this will equal 0. So I've proven the second thing, that the inner product, with itself is 0 or positive. Really only positive. The only way it is actually 0 is if that function is 0 itself, right? Then the dot product with itself, inner product with itself will be 0, okay? So I showed all 4 properties, and that's it, right? So the inner product on the closed interval from a to b, that of continuous smooth functions, going to the scalar r, given by this definition, so taking a function from here and another function from there and multiplying them together by integrating them, is a dot product on that closed interval, okay? So there's kind of a lot of jargon, but disregard the jargon, just focus on what it is that we did. We just showed that the 4 things are true for this. That's what I'm really looking for, is can you kind of start with an argument and end it by not skipping step, by not assuming some algebra, right? Just kind of keep the flow very smooth, right? So that is our proof. So since the dot product is also an inner product, okay, for 1, that the properties that we formed for the dot product are true in general for all inner products, right? So when I say 1, I mean talking about this, okay? This is the one I'm referring to. Remember, the dot product is your weighted inner product where the weights are evenly distributed, so this d is just I, okay? So this is your standard dot product, right? That was our definition of the dot product. Okay, so since the dot product is also an inner product, because 1 is the same thing as 1, but with your diagonal matrix, the identity, that the properties that we formed during that dot product section are true in general for all inner products, right? So I said this at the beginning of the video, so I'm just reiterating it now. So all of those things that we had before for dot products, we can do now. So there's several things, right? Things like triangle inequalities, the Cauchy-Schwarz inequality, norms, projections onto a subspace, Graham-Schmidt, right? Most of those we're going to cover in the next video, but all of those things hold true for all inner products, okay? So we're just going to go through a couple of those, right? Examples. So if V is an inner product space, so this is a vector space with an inner product defined on it, so it's an inner product space. And U and V are vectors in that vector space. So I don't know if they're actual what we call vectors, matrices, functions, right? Whatever form they are elements from that vector space, okay? If the inner product between them is 0, then U and V are orthogonal in that vector space. In that inner product space, okay? So again, we're taking that from dot products, right? The norm of a vector V in an inner product space is the same definition, right? It is the square root of the inner product of V with itself. So for dot product, it was v dot product v. Here it is v inner product v. Okay, so again, all the rules are the same, but the math to show them may include integrals or polynomials or traces of A transpose B, or however it is that we're defining our inner product on our vector space. Okay, so next definition that holds also is that the projection of U onto V in an inner product space is the projection of V onto U. So same formulas, but instead of dot products, right? Instead of dot products, right? Your norm squared is going to be V dot product, V inner product V, and you're going to have U inner product V on top, and you're still going to multiply that across your vector V, because that's the one you're projecting onto, right? Remember, this is a scalar multiple of V itself, right? So again, same rules for dot products. It's just that everything is an inner product now, right? U inner product V, norm squared of V, where it's just, this is really just V inner product V, right? The Pythagorean theorem is still true, okay? V is an inner product space. Then for the two vectors U and V that is in that inner product space, this inequality holds, right? So as long as it's a right angle between those vectors, that you have, you know, the long side squared is the sum of the square of both sides together, right? So square one side plus square one side, norm squared, right? The length of them. So the Cauchy-Schwarz inequality holds as well, which is the absolute value of the inner product is less than or equal to the norm of each individual vector multiplied against each other. Okay, and the triangle inequality is in an inner product space. The norm, or the length, of U plus V is less than or equal to the norm of V times the norm of U. Okay, and again, this is using whatever the inner product being defined is.